All right, I guess we'll go ahead and get started. So it's my pleasure to introduce today's CRB seminar speaker series, Professor Farrell Helbling, who is currently assistant professor in the Department of ECE at Cornell. Before that, she was a PhD student and a postdoc in Rob Wood's lab at Harvard University. Farrell's work is looking at how to enable autonomy in very small robots. So looking at design for power, communication, sensing, et cetera, on centimeter size robots or smaller. Examples for this are the Hammer robot, which is a 1.5 gram crawling robot, and the famous RoboBee, which is approximately 100 milligram flapping wing vehicle. So I'm happy to hear more about your work, and please join me in welcoming Carol.
Hello, everybody. Thank you, Mike, for the introduction. As Mike said, my name is Farrell Helbling, and I work on autonomy for insect scale vehicles. One of the big projects that I've been working on, one of the big platforms that I work on is RoboBee. And so this was the power autonomous work that I did in 2019. And so I'll talk a little bit about how we actually designed that system today. So science fiction has a lot of ideas about what autonomous flapping wing vehicles could do. And these are mostly examples that people send to me over time. Yes, I look out for them, but a lot of times my dad will send me a video. Like, did you see this? And I was like, no, I didn't, but thank you. He was very upset about Black Mirror from 2017. But I think it's actually a pretty good example.
Sorry, why was he upset?
I think he was just scared about it. He's like, what are you doing to society? I was like, this isn't even about RoboBee here. It's about people. Eye in the Sky in 2016. I think that this was playing on the plane to one of the conferences that I went to because every single person asked me about this movie and I had never heard of it before, and I watched it on the plane on the way back. G.I. Joe Retaliation, I think, is one of the sillier examples. This is a firefly that eventually this combustion actuator is going to explode, and I don't think that it would actually harm anybody based on the size of the payload, but if you have enough of them, it could. When I was a kid, I very much loved Minority Report in 2002. This is not a flying platform, this is a crawling platform. So he basically throws these discs off of his belt. They turn into these walking spiders and they go off looking for Tom Cruise, who is hiding somewhere in the building. If you have not seen this movie, I very much recommend seeing this movie. I think it is a very good film. And then as a kid, I watched Richie Rich in 1994. And this is a very good example of a small autonomous RoboBee platform. And the thing that I like so much about this clip is that you have this scientist who has developed this, $1 million platform, and he's so confident in its ability to fly around the room that he hands the controller to a complete and total novice, right? Like, Richie is smart, but I would not hand RoboBee controls to a child. And I kind of like thinking about it in terms of, what we're searching for in the future, right? Like, if I want RoboBee to be outside of the lab, if I want more than my students to work on it, or Rob Wood's students to work on it, or anybody else who's working in this field, you need to make it more plug and play, right? And so what we see in the space, and you can see it in CRB, you can see it in a lot of different areas, you have robot arms, you have these quadrupeds that can wander around, you have these quad rotor drones. And so if you can buy these platforms off the shelf, many different people can study many different aspects of robotics, of autonomy, of path planning, higher level questions that we can't yet do with insect scale robots. If I look at micro robots and the state of the art of the field, they're delicate, they're tethered, and they're very specialized. Okay, and because I've been in this area for many, many years, I can look at all these pictures and say, oh, I know how that was built. So I know exactly who built it, right? And so we're trying to see, can we make these things a little bit less custom and a little bit less fragile in the environment? And so what people have been doing for a number of years is looking at different locomotion strategies. So if I do a 4-wing vehicle versus a 2-wing vehicle, how does that affect my locomotion? If I think about different actuation strategies, so if I use ionic propulsion versus, low voltage electromagnetic, what are the implications for me in my power system design? Okay, so you have to kind of look at the entire stack when you're building something so small, right? Every single milligram that you put on these platforms is basically a question of, are you going to be able to fly or not? So I build autonomous micro-robotic platforms that span a lot of different areas, some of which I cover, some of which I do not. Some of the main things that I think about in my lab are micro and mesoscale manufacturing. So how do we actually build the articulated mechanisms necessary to either flap our wings or move our legs? How can we think about power storage and amplification? So I'll spend a lot of time talking about some of the power system design that I did to make RoboBee untethered. And then also thinking about custom sensors and ICs, okay? So I don't really do a lot with IC work. I work with people who do VLSI, but always thinking about how we can reduce power, reduce compute onto our very small platforms. Some of the very interesting opportunities that we can get at the centimeter scale is we can get very interesting locomotion strategies, right? So surface forces scale much more slowly than inertial forces. So we can get things that climb up walls, that can climb on ceilings. And sticking is something that's very easy to do at our scale. So this is an example of a hammer robot that is actually climbing upside down inside of an engine. You can start thinking about collectives. So this was a kilowatt picture from some of Mike's old work. We can also use them as platforms for biological study because you don't really want to put a bee inside of a tube and spin it around many times. Like, what can we actually learn from some of these small scale systems? Also do things with planning and estimation. How can you do it on a very low compute platform where you don't have an operating system? We don't have ROS on board, right? Everything I'm doing, I'm programming in C on a very small SD microelectronic microcontroller. And then finally thinking about system level optimization. Again, because every milligram that I put on board is either going to determine, am I going to fly or not? So when I first joined Rob Wood's group at Harvard, they had just achieved hovering flight. Okay, so this was 11 years ago. They had the RoboBee platform. Sorry, the video looks better over there than it does here. But this tiny vehicle is 80 milligrams. So in terms of scale, it takes about 32 of them to weigh a penny inside of your hand. It's a very lightweight vehicle. Back in 2013, it had a total payload capacity of about 40 milligrams. So you're thinking about like 1 3-millimeter IMU that you can put on there and nothing else. This guy has a wingspan of about 3 centimeters. You can make the wings smaller and just flap it at a higher frequency. So I don't really like thinking about it in terms of that type of size scale. Actuation, it flaps at about 180 volts and it consumes about 20 milliwatts of power. Okay, that's just the actuator, nothing else on board. Okay, this system is tethered. Okay, and so what I started thinking about was, okay, we have these challenges for centimeter scale robots. We have our current state of RoboBee is trapped inside of this motion capture arena that is providing position and orientation information. Tether off board is providing power and control signals. And I wanted to break this down into these 3 constituent components. Okay, so what kind of sensors can I put on board the vehicle to allow the vehicle to sense different states? How can I change the design of the vehicle to carry more payload capacity without also increasing the amount of power that it was consuming? So there was a lot of work that went on between the very first generation of the Bee to, we called this Big Bee, and then we have RoboBee X-Wing, which I will talk about later in this talk. And then different power strategies as well. So either thinking about custom battery solutions, off-the-shelf solar cells that we can buy pretty cheaply, and then step-up converters. Okay, I haven't gone into the actuation strategy yet for RoboBee, but we do need to step up the voltage. So that's what these 2 flex PCBs are. I'm going to talk a little bit about the sensing work that I did, but for the sake of time, I'm not going to spend too much time on that area. I'll get pretty in depth into power because that paper came out in 2019 and then we had a pandemic, and so I don't get to talk about it very often. So I'm going to talk a little bit about that as well. And then I'm going to get into some really cool and interesting locomotion strategies and opportunities that we can do at this scale. So in order to understand how we embed the electrical system, we need to understand how the mechanical system actually works, okay? And so we do these mesoscale manufacturing methods where the majority of the body is made out of carbon fiber, and then we have flexures that act as gearing and transmission systems, Okay, so embedded in between the carbon fiber, you can see these like thin yellow lines. That's just a polyamide flexure layer. Okay, when you fold it into different configurations, you can get a 4-bar linkage. Okay, which can translate back and forth motion of your actuator to flapping motion moving forward. Every single piece that you see here is custom made inside of the lab, except for these Vicon markers, which we buy off the shelf, but then we do pull the plastic out of them to get them to weigh even less than they do normally. And then, of course, we have a power cord and a tether. So I'm going to step through each of these components. So the first thing that we do is we fabricate both the rigid material, but we also want to embed these flexible layers so we can create hinges, right? So we individually pre-pattern every single layer, okay? And this is the most simple design that you could possibly make. This is the first thing that I make my students build when they come to the lab. So we pattern each individual layer. We have a rigid layer, an adhesive layer, and a flexible layer, okay? And then the other side, also adhesive and rigid material. When we heat press and cure this material, we then get one solid stack, okay? And by pre-patterning these, we can expose the different areas of polyamide that we actually want to bend, okay? Once this is done, we laser cut and release these bridges, and you get one hinge at the end, okay? You can create many hinges in series, you can create them in parallel, you can create these different types of mechanisms. RoboBee is powered using piezoelectric biomorphs. Why do we do them? They're small and lightweight, so each actuator is 20 milligrams. They have high energy and power densities, about 2 watts per gram, and they also have a very wide bandwidth range, okay? So you can operate them anywhere from 1 hertz up to 1,000 hertz, okay? And so I've never actually run them up to 1,000 hertz, at least not when they're loaded inside the vehicle. That is way past the resonance of my system. I will crack my actuators. But it's nice because you could build a small crawling robot and operate it at 10 hertz. You could build an even smaller crawling robot, operate it at 40 hertz if you want to. And the RoboBee can operate anywhere between 120 and 170 hertz, okay, depending on the design of the transmission and the wing that we want to put on. So it gives us a lot of flexibility. We then did a lot to study the propulsion strategies. So what are the different wing sizes, the wing shapes that we need to actually generate the vortices, shed them, and generate the lift capacity for the vehicle, okay? A lot of work went into the vehicle design to actually increase our overall payload capacity. You can make improvements in the wings, but the overall benefit of wing improvement is significantly smaller than changes to your actuator, et cetera. Okay, my favorite part is actually assembling the vehicle. We do this under a microscope with tweezers and glue. My students hate it, and that's okay because I will do it. Or I will at least step in while they're trying to learn this process. Some of these things we can combine. So there is the pop-up book method that was developed in Rob's lab in 2012, but while we're iterating through different designs, I kind of like having it more modular. When you're building a pop-up, a lot of things have to be pre-designed inside the scaffold, and so you actually can't swap things out as easily. So everything is done under a microscope using tweezers, and then we apply very fine coats of glue and epoxy to make sure that everything stays exactly where it needs to. Once this is assembled, we then test it. As I said, each wing is powered by a single actuator, so we can flap them at different frequencies. We very rarely do this. We can flap them at different amplitudes. And in this way, we can generate the torques necessary to controllably fly. Do you need me to admit this person in the waiting room? No, no. Perfect. I think I got rid of it. Don't know how to get rid of this though, guys. I'm sorry. That thing is going to live. So how do we actually control the motion of the vehicle? Like I said, we can vary the frequency and we can also vary the amplitude that is provided to each wing. Okay, so in order to control pitch dynamics, we just change the mean position of the wing either forward or backward, and that just my body forward or back. Like even as I'm telling you this, right? Like my body naturally wants to move forward or backward. Roll, we just flap one wing at a larger amplitude than the other. That causes asymmetric forces. Yaw control, you actually can't do this at resonance. You have to move further away from resonance. Resonance will actually filter out this split cycled signal. But what you do is you just flap one wing forward faster than the downbeat. And then on the opposite side, you do the opposite. So you would flap up very slowly and then quickly on the backside. You can do this in a pool if you are just hanging out in a pool and you want to spin around really fast, test it out. It actually works. But again, this can't happen around resonance. This is a second order effect, which gets filtered out by our system. Yeah.
Do you know if actual bees flap at resonance?
Oh, that's an interesting question. I'm not sure. I mean, there would be a lot of energy savings around flapping at resonance, so I imagine they would want to. But I don't know. They also don't necessarily have the same type of flapping control here. Like they have one big power muscle and then small control actuators on the side to change the angle of attack of the wings. We can do that. It's just significantly more complex to build and not as repeatable. So
I mean, what is the resonance of a natural bee wing and how does it compare with yours? Do you know?
yeah, so bees will flap somewhere around 110, 120 hertz.
Okay, I understand.
Yeah. This vehicle does, we flapped at a higher frequency later. So some of the power autonomy stuff, but
Yeah,
we're up to
right.
165. Totally fine. Okay, so we build it, but because everything is built by hand, you have all these open loop effects where it's just gonna crash into the ground, okay? And so we do this thing where we keep trying to tune the parameters until we get that kind of straight up and down flight, okay? At that point, we're kind of like, okay, we've tuned out all of our biases. Once we have that, we wrap a controller around it. So again, we have these motion capture markers that are constantly tracking the position and orientation of the vehicle. And then we have this onboard tether here, which is sending control signals and also power to the actuators, okay? So all of this is still trapped inside the motion capture. Yeah.
The motion capture tags have any significant drag in the system.
Does it have any, like a lag in the system?
Drag,
Drag.
yeah.
Oh, the tether. Does the tether have drag?
Do the tags make any drag that causes the thing?
Oh, no. No. And the tether also, honestly, I think would probably have more of an effect. But we did a lot of studies where we actually just kind of like dragged the tether under the vehicle, and so the controller can kind of compensate for it. But it would be another thing that I don't have to worry about if it was autonomous.
Question about
Yeah.
that. So the time constants here must be tiny. And so I imagine latency in your sensing or even the frame rate of your sensing.
Yeah.
Are pretty important. So
Yeah,
what were those approximately?
So the Vicon system is somewhere around 500 hertz and it has about 20 millisecond latency, which is not excellent, but it was perfectly adequate for some of the control work that we were doing here. The sensors that I can buy off the shelf are providing feedback significantly faster than what my Vicon cameras can do. Obviously, they're not going to be as precise, and so they're going to start accumulating error, and that's something that I had to deal with. But
You can do control at 20 milliseconds of lag.
Yeah. You absolutely can, especially for something like hovering where you just want to kind of stay in place. And then if we want to do any type of like fast movement through the environment, we kind of split it into like multiple hovering waypoints where just like hover, 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 and then it just moves into that position, either by pitching or rolling. Okay, so everything exists inside of this motion capture arena. And then just for scale, this is the beat down here. This is actually an image from the Vicon arena that I had during my PhD, but I built an exact identical version at Cornell, so the images would look exactly the same. I just didn't take another photo. Basically, this is all of the equipment that is required to fly RoboBee. Okay, and this is one of the real limiting factors of why we can't like provide other people the capabilities of using it. We can step through the whole thing, right? So we have our motion tracking system, which is providing position orientation information. That is being sent to this off-board controller, which is creating the actual Vicon object. It is sending position orientation information to our control computer. Within our control computer, we have an altitude controller, a lateral controller, and an attitude controller, so we can determine our desired orientation. And then that also computes the signals that we want to send to the actuator. Again, because it's coming from the computer, it is very low voltage, somewhere between 3 and 5 volts. So everything gets stepped up through a high voltage amplification system down here to about 200 volts necessary to fly the bee. All of that gets flown directly through this very fine wire tether to the bee. So if we actually look at some of these challenges, first going to think about sensing. Okay, so our current sensing system is off-board motion capture. It records 3 axes of position, 3 axes of orientation. It provides feedback at about 500 hertz. We have thought about like, how quickly do I actually need to do this? And so we will subsample Vicon down to kind of give us a minimum feedback necessary. But again, everything we get off the shelf is doing well more than 500 hertz, so that's okay. And a latency of about 20 milliseconds. And we used to joke around and say that this is like training wheels for the RoboBee. So inside of our control architecture, we have our motion tracking system. With the original vehicle, what we wanted, and I don't know how to get rid of this, I'm so sorry, is a payload capacity about 10 milligrams of sensor, okay? We can do different sensor combinations, but we are really looking for very small sensors that we can put on board the vehicle. And the more sensory information we have, the better. Again, the wingspan is about 3 centimeters. That is going to dictate how small of a sensor that we can actually put on board. This top cap up here that you see is about 1 millimeter by 3 millimeters. Okay, so if I even just put like a 3 millimeter IMU on top, that kind of looks like a hat or like a very funny hat that sits on board. Flapping frequency is about 150 hertz. So this is going to just add repetitive noise into the system as we go. You can see it in the accelerometer and the gyroscope data that we have. This power number is like very optimistic, where we would like it to be less than 5 milliwatts, because again, RoboBee cannot carry a battery up to this point. It can carry onboard solar cells, but everything that is kind of statically not providing propulsion is just something that is going to eat power out of our system. Attitude bandwidth is somewhere around 100 hertz, so we can, affect changes in attitude at about 100 hertz. Lateral bandwidth, significantly slower. Okay, so I can get significantly slower sensors for altitude and for lateral dynamics than I need to actually stabilize my upright orientation. So I did a sensor survey of things that we can buy off the shelf and things that we can just put on board custom. So insects use ocelli. These are light sensors. They're sun compasses that sit on top of bees. They have 3 sensors that sit in a triangular pattern. This was using 4 photodiodes, sorry, across 2 major axes. And just by measuring the difference in light intensity between these axes, you can get full orientation of the vehicle. You can also buy off-the-shelf IMUs. You can buy magnetometers. This was, I think, the very first conference paper I worked on, and I thought I was like so smart by soldering directly onto the sensor instead of like putting it on a PCB. This is very silly. I don't recommend. But I think that like the first conference paper you actually do, you don't realize how silly some of the stuff you're doing is. But yes, that's what I did. I thought it was very smart. Also thought about proximity detection. So proximity sensors, you can either measure the amount of intensity that you see with your photodiode, but you also have time of flight sensing, right? Where you can measure the amount of time that it takes for a light source to come back. They both weigh approximately the same amount. They're about 20 milligrams. Optic flow is just a very low resolution camera that is detecting the velocity of known patterns in the environment. We really benefit from minimally invasive surgeries and endoscopic procedures because you can buy very, very small cameras nowadays. So this is a NAN-IC. This is 1 millimeter by 1 millimeter by like 1.3 millimeters. It's a 250 pixel by 250 pixel sensor. You can get it in full RGB if you want. You can also get it in black and white. And so this is something that I'm currently working on now. And you can also put on a very small antenna and string gauges too on the back. This obviously never flew. This would be a very silly antenna orientation if you wanted to fly, just because you're greatly affecting the center of mass. But yeah, these were all the different sensors that I looked into during my PhD. So I'm going to show 3 examples of these flight systems. So the first one is just attitude control with an onboard IMU. So you can't tell, but there's an IMU that's just sitting on the top of this vehicle. It's just a little hat. And so all we wanted to do is to take off and go to this set point here. Okay. This again is playing at 1/8 speed. We're filming this with a high-speed camera, and it can hit that set point, okay, and there will be drift, and it will try and come back to the set point. But eventually, the drift, the integration error that we are actually doing, because we only have one gyroscope providing information, will make it so that the vehicle can no longer properly estimate its orientation. Okay.
Is IMU sending data back over the tether to the central?
Yes. Yes. So you can kind of tell there are 2 tethers here. So you have one high voltage tether that is providing the control signals, and then you have another low voltage tether that is providing the sensing information. But this latency is significantly less than the 20 milliseconds from before. And this is also providing information at 1,000 hertz compared to the 500 hertz of Vicon. So we use kind of Vicon as a benchmark for anything that we wanted to do, because we know we can control it with that latency.
So with the propulsion at the top and the body below.
Yeah.
Does that help stabilize it in hovering because it's sort of like a pendulum instead of an inverted pendulum?
Exactly. And so putting the mass on the top of the vehicle was stupid.
Okay, that's what I was gonna ask.
Yes. Again, I learned from this, all sensors now are on the bottom of the vehicle and not on the top. Very good question. But I liked the idea of the top hat on the system. So it was honestly the easiest place to connect, because the legs are very, very lightweight. And so the B is 80 milligrams. The sensor actually weighed 35 milligrams. And so it was just bending the legs down. But putting half of your mass on top made the control problem significantly harder. We also did altitude control using an onboard time of flight sensor. So time of flight sensors are proximity sensors that measure the amount of time that it takes. This was just with a very simple PID controller. So it's hovering around the set point because I didn't tune my PID controller properly. But even if I just compare this to the straight Vicon flight, very similar to before. Here, the time of flight sensor is hovering right underneath it. Okay, so we have thicker legs that are keeping the sensor in line. And again, everything is being sent to the offboard computer and then coming back through the control system. Yeah, okay, so these are the 2 sensors. This work has been very much built upon by Sawyer Fuller's group at Washington State, where they're, not Washington State, at the University of Washington, where they're thinking about minimal sensing suites for these small scale platforms, specifically for proprioception. So I think they combined both the IMU and the time of flight sensor and an optic flow sensor together. Yeah.
The bandwidth for altitude control quite a bit different from lateral.
Yeah.
So.
Or from the attitude control.
Okay,
Yeah.
so is that a mechanics issue? Is that a control circuitry issue? I'm just looking at the.
So that's a mechanics thing where you actually don't need to provide as much feedback. So this sensor is not providing information at 1,000 hertz. This is providing information at about 20 hertz. And we actually just turned Vicon down where it would only provide information every 20 hertz, and you could get a stable system if you wanted to. I mainly just rewrote the controller for altitude just to simplify it for the purposes of this paper. But yeah, that's entirely mechanical based, not compute based. Simplifies my compute significantly. I will take it. Something that I worked on was the idea of using cameras for exteroception. So this camera is sitting on the back of this actuator. And so as I twist this checkerboard pattern in front of the bee, the camera is trying to follow the orientation and keep it straight in line. Okay, and this is something that we actually see bees do when they're approaching an obstacle. They will actually fix their head and move their body around it so they can keep the obstacle perfectly in line. So this sensor was measuring optic flow, and then there was a little bit of a lag and a delay here. But I've taken this same camera system that we have here and integrated it with an ST microelectronics, I think it's like a G series board. It's not currently existing on the robot. It is consuming significant amounts of power to do so. But we did a real-time end-to-end system demonstration. And this was just a minute gyro, so I'm not going to get into it too much. Where we have 4 lights inside of our environment. These are just LEDs. There's really nothing special about them. We kind of waved this, the camera and the microcontroller around the arena in a figure 8 pattern while also changing the height of the system. And so you can see that there is some noise in our estimate, but you can get full orientation and position information at about 17 frames per second. Okay, so it's a little bit slower than what we would want for a RoboBee platform, but it could also be used as a secondary sensing system for a high-speed IMU or provide additional feedback on board. And this is all being done on the microcontroller. There isn't any additional compute happening on board. So we're very excited about this result. Okay, so that's kind of what I did in the sensing realm. I was on a lot of different papers from other people, but for the sake of time, I'm going to transition pretty quick into power. Because I think that result is just significantly more fun. So in 2013, when the original Bee took off, it could carry 40 milligrams of payload. This is not enough for any onboard power system that we want to put on. Okay, the smallest LiPo battery that I can buy is 330 milligrams. Okay, so 5 times the weight of my vehicle, and that doesn't include any of the step-up components that I need. So how can we actually increase the thrust of the vehicle? We want to increase thrust, but we don't want to significantly increase the weight of the vehicle, and we don't want to increase the overall power consumption of the vehicle either, okay? Because that will also have implications for whatever power system I put on board. So we increased the actuator and transmission stiffness, which led to a pronounced resonance inside of the system. So we had a new operating condition that was about 190 volts and 170 hertz, okay? The overall load was 28 milliwatts, so we increased it from 20 milliwatts, but it could lift 170 milligrams compared to the original 40, okay? So this was work that was done by Noah Jaffris, who eventually was a co-author on the Nature paper that I'm going to talk about. You can't see this, but it has a very, very small wingspan here. And so you can see that just to hover, it doesn't take a lot of energy to do so. So now instead of talking about systems, we're just going to talk about how do I generate a waveform and how do I step up that signal. So we use these piezoelectric actuators, these PZT bimorphs, and we want to generate a high voltage time varying signal. So same thing, just a different picture. PZT bimorph just means you have a layer of PZT, a conductive layer in the center, which here is carbon fiber, and then you have a bottom layer of PZT, okay? This bottom layer is being charged to ground, the top layer is charged to some bias voltage, and then the central layer is our time varying sine wave. Okay, and Purpleson in 2011 wrote a paper about how you can actually do this at small scales. Okay, and so this is a tapped inductor boost converter with this like half bridge switching stage on the other side. And he estimated that the mass would be about 100 milligrams and the input power would be about 100 milliwatts for a 20 milliwatt vehicle. Okay, so I said, we're gonna start here. Let me actually build what he suggested. Before I did that, I also thought about what our power options were. So I worked a little bit with somebody in the lab on custom batteries, very thin scale. When they were in their full housing and we were testing them, they showed a power density of about 1 kilowatt per kilogram and a mass of about 100 milligrams. But as soon as we actually got them down to the mass of 100 milligrams, they could no longer deliver that power density. I do not understand enough about battery chemistry to explain what was happening. But this was not a feasible option. So we moved into photovoltaics. Each of these cells weighs approximately 10 milligrams. It has an overall efficiency of about 30%. And each cell can provide 10 milliwatts of power under one sun. Okay, so one sun, not in Australia, but like on a general sunny day here, about 1,000 watts per meter squared. It can provide 10 milliwatts of power. So very simple equations for power autonomy. The total lift of your vehicle has to be more than the static payload of the bee, your source, and your drive stage. Your total power has to be less than whatever power your source can provide. And so I did this very quick thing where I said, okay, if this is 100 milligrams and I have 60 milligrams of solar cells, that mass calculation works. But what it means is that I now need to provide 2 suns in order to take off. Okay, that's the only way that my power budget is going to work. So I built these in discrete components. I made the Flex PCB in-house. We have an LPKF. It's very easy to do. And so when I did this, my mass was nowhere near 100 milligrams. It was 185 milligrams. And most of that was just to stabilize the voltage coming in from the solar cells. So we had 20 milligrams of capacitors that were just sitting here, and I started stacking them like a leaning tower of Pisa to try and just stabilize my voltage at the lowest mass possible. My input power also was more than what I anticipated. It was about 150 milliwatts compared to the 100. And most of this was because the microcontroller unit was pulling 30 milliwatts of power. And this was mostly because we were running the clock at significantly high speeds because we wanted to flip the transistors very, very quickly. Okay, and so when you run microcontrollers, the current consumption is based on your megahertz of clock rate. What we showed was that our flapping kinematics are exactly the same. Okay, so in theory, this would work. We just could not take off. Okay, it's 25 milligrams over our mass budget. So how do we actually generate a high voltage time varying signal with lower mass? You can do it using different boost converter topologies. So if I have a unimorph, I can simplify the number of components that I need in this switching state. And I can just have 2 signals I need, QL and QH. But I have a bimorph, okay? And so I would have to take that and double it, okay? We could absolutely do that. And in order to get that, we just then run these 2 plates out of phase with each other. The problem is that because I don't have an alternating drive strategy, I had to basically adapt the work that Carpelson had done in 2011. Because we want to prevent depoling of our actuators, VA, the voltage that I apply to A, always needs to be greater than the voltage that I apply to B, okay? This isn't too much of a difference. So instead of running these 2 waveforms out of phase, VA is constantly getting this signal. VB is either clamped or it's just passively following the voltage of VA. So we had this additional QS, which basically clamped the voltage of VB, the base. But we had 2 flyback converters. Flybacks are what the topology was on the previous slide. We had an additional clamp that shut off this bottom plate of the PZT actuator. And so we were able to build this system and only send 1 signal to 2 actuators. Okay, so I could get it to take off, but I can't actually controllably fly untethered. Okay, I'm gonna show you a video that I still think is very cool, but no, I cannot control its flight. Okay, it will take off, but that is it. So I created a new drive signal, and I also greatly simplified the switching strategy. So I could use a simpler microcontroller than what I had. So before, I would have needed 4 suns to power 150 milliwatts. Now I just need 2.5. I reduced my mass by 30 milligrams. My dimensions were a little bit larger, but my overall power consumption reduced from 150 to 110 milliwatts. And my overall efficiency also improved, okay? At the cost of not being able to generate multiple signals to the vehicle. The waveform did not look the prettiest, but if you actually just looked at the FFT, we were pretty spot on compared to what we were actually generating with clean sine waves. So we developed this first untethered flight, and I watched this video probably for 15 minutes to be like, did it take off? And it goes up a little bit here, and we could not agree on whether or not the tether actually pulled it up or not. And the person that I was working with, who was working on the vehicle design, was like, you got to get this to be even smaller. And I was like, absolutely not. Okay, I've already saved 50 milligrams. I have shaved off 40 milliwatts of power. We have to look at a vehicle redesign. So we created the RoboBee X-Wing, which had a new actuator design, which increased our force. But by increasing force, you also linearly increase your power. Okay, so what we wanted to do was we just decreased our wing velocity. The way that we did that was we just went from 2 wings to 4 wings. So each actuator now just passively controls these 2 wings. Okay, so these 2 wings just follow each other. There's nothing going out of sync. We're not doing clap and fling. This is just moving in one direction. So the mass of the system is 90 milligrams. It did not change the overall load. We're still at 28 milliwatts. Now my total payload capacity moved from 170 milligrams to 215 milligrams for the exact same actuation signal. So the board here, the signal generator, is sitting below it so that we can match the center of pressure to the center of mass. This allows us to get these straight up and down flights. And then our solar array is spaced so far away from the bead just to prevent any type of sealing effect on board. The other thing that we could do is just create a ring around the wings, would have provided the same thing. So this was actually our first untethered flight. So in real time, it looks like this. When you slow it down, as soon as I turn the lights on, the energy provided by the solar cells turns on our generator here on the bottom. And I immediately start sending signals to the vehicle, okay? As the power starts ramping up on the lights, because again, there's just like a delayed effect on the lights, you get this kind of slow increase, and then it will actually take off all the way for many, many body lengths more than it does. And it could do this repeatedly, okay? We had a tether on board for safety, so it would basically go up into the light, fall back down. We could do it over and over and over again. But again, we don't have the ability to actually control the flight yet. But this was the first untethered flight of an insect scale vehicle to date. And we were very, very excited about it. I don't think I hyped it up enough. This was very hard. This was incredibly, incredibly hard. C was there. She watched it happen. It was very stressful for everybody involved. This got published on the cover of Nature. They created this kind of moving cover that we were all very excited about. We were very concerned about being sued by Disney because we had an X-Wing robot. The title that they created was Flying Solo. And we also, in the article, because we can fly in 2 suns, they said we could only fly on Tatooine. And I was like, this is too many Disney references. We didn't even do it, and it made us very stressed. But Disney never came after us, so I don't have to worry about it. But this was the first untethered flight of an insect scale micro robot. Total mass on board was about 259 milligrams. It was about 2.5 to 3 suns, and we just exploited passive stability to get upright flight. Thinking about different ways of going outside, you can improve actuator efficiency. You can also improve the overall voltage by just using multi-layer actuators. This is something that we're actually working on in the lab right now, moving from 200 volts to 100 volts. And then thinking about a new vehicle design to increase the capacity. One way that I've currently gotten around this is thinking about new locomotion strategies. So we have a lot of challenges for centimeter scale robots, but we also have really interesting opportunities in insect scale systems because of the size. We have impulsive locomotion strategies. So this is something that I've been working on with Rob Shepard and Cam Aubin, who's now a professor at Michigan. And so you can get these really nice combustion actuators to do jumping or kind of scuttling across the surface. You can also have high strength weight ratios. This is some of the work that I did on the camera system that I now have new crawling systems that have not yet been published in my lab, but this is 400 milligram system, but it can carry up to 3 grams on board. So the force that is actually being provided by the actuator is exactly the same as the hammer system. It's just half the size. I'm gonna pause this. We can also, yeah.
The impulsive locomotion side. So you're really looking a lot at power and energy, and there's always this debate, and there's been a few science papers on the efficiencies of hopping or
Sure.
surfacing across water with flying fishes, etc.
Yeah.
Do you have any insights into power efficiency over land or water based on
Yeah.
your very detailed calculations here?
So one of the interesting things about impulsive strategies is that you don't have like the time function. So a lot of power is being sunk into microcontrollers, right? That can that are computing real time power metrics or actuation signals. You don't need that with impulsive strategies, which is really nice. And it's not something that I would say is like the best way of traversing a space, but because you can like very slowly provide power for like a very quick burst of energy, depending on the actual design of the actuator, it could be more power efficient than what we're thinking of. We can also collide with things really easily because we are low mass. And one new robot that I'm working on in my lab is this interfacial flyer. And so taking something that is very similar to RoboBee, putting 3 of these passive legs on the water surface and allowing it to skate across the water. I like this platform because you can separate the thrust problem from your payload problem. Your payload problem is now completely dependent on the size of your legs. And your thrust will just dictate your speed across the water. Just for the sake of time, we've all seen water striders. We know that they work across the water surface. Importantly, if your Bowden number is less than 1, then surface tension starts to dominate over your inertia, okay? And you can stay trapped on the water surface. Oh my gosh, that startled me. Interfacial flight is one example of a water skating capability. This is a water lily beetle. I did not take this video. I apologize for the quality of it. But it will flap its wings, the middle pair of legs will lift up, and the speed across the system will slowly increase. And what the paper found was that water drag plays a significant effect over all other forms of surface tension. So we have 3, this is the Gamma Bot, new vehicle. We have 3 passive legs that keep the vehicle on the water surface. Horizontal thrust is generated by the flapping wings. Total mass is about 112 milligrams. It can carry about 419 milligrams of payload capacity. So now we're getting into like, could I carry a battery on board if I wanted to? Here, the actuation signal is significantly less. We only flap at about 150 volts, and it can move up to 15 body lengths a second or a meter a second across the water surface. Physics on the air-water interface. Again, you have thrust force, you have drag forces on the leg, you have capillary forces, surface tension forces, and drag on the body, air drag on the body. Water drag, all these forces work on slowing the robot down. And what we found was that water drag significantly dominates these forces by multiple orders of magnitude. So it's providing significantly more force than capillary forces or surface tension or even air drag on the system. And so we looked at the different experimental performance, and we saw that our behavior very well matches our predictions here. So this is just 2 little models that we had when we had the signal completely going off and we eliminated the air drag on the body. And then when we had the signal on, what we noticed though was that we had this secondary increase in velocity that was happening. And that was actually being generated because our front leg is generating this wake to the 2 back legs, and it's creating this like low pressure field in the back leg that's increasing the velocity past what we can model and predict here. The wider we got our legs, the faster we could get this transition to happen. So in real time, again, it's moving at about a meter a second. This is slowed down since 0.04x. And I like these videos just because you can see the effect of the ripples on the water surface. This is still tethered. I'm currently working on untethering it with my students. We can also get it to turn left and right by providing asymmetric forces on the vehicle. can get a left turn. We can also get a right turn. I do find these lines to be mesmerizing. So in addition to doing untethered performance, we're also thinking a lot about these high frequency ripples that we have here, and how we can actually embed communication strategies between multiple robots, or can we sense obstacles in our environment by thinking about these ripple patterns that are being generated. So yeah, these are some of the cool new platforms that we've been developing. Just kidding. I also like these tools because they're very interesting for external engagement. I worked with Mike at the Museum of Science in Boston. They finally killed this. This no longer exists. It's so sad. But it's also been at the Smithsonian. It's been at different aeronautics spaces, World Economic Forum. I had to do something for Facebook back when Facebook was still a thing. And so, yeah, if anybody has questions, happy to answer.
We have time for a few questions. Questions?
Is there any advantage to having the wings close to the water versus further away?
Yeah, so that's something that we're actually thinking about because we can do a lot with ground effect studies. So Jane Wog is also at Cornell, and so we're doing some work with her to think about these, or hope to in the near
Is
future.
it better to be in the boundary layer or out of the boundary layer?
I think that we could get interesting performance if we're within the boundary layer. But my initial inclination is we want to be outside of it because then you can better control your performance, but not sure. Interesting physics happen that I don't fully comprehend as an engineer. Yeah.
Why did you choose to track a reference pose for the bee instead of let's say a trajectory? Because you don't always need to hover as an insect. You can kind of like track the trajectory instead of having to like go from point to point.
Oh, interesting question. I think it was just to simplify it, and we always want to make sure that the vehicle is in upright orientation as much as possible, because if you pitch or roll too far away from your upright position, it's very easy to go unstable afterward. So it's just a easier way to stably move through the system. Yeah.
How long did each of your robots typically last? Like, how long can you use it? Months, weeks, days, hours?
Oh, if they're tethered, months. The first thing that's going to break is probably a wing hinge. And those can be easily swapped in and out. Eventually, like you'll get some plastic deformation in the hinges of the transmission. And so then the risk there is that you've lowered your overall resonant frequency. And if a student doesn't catch that the resonant frequency is dropped and you operate it past resonance, you'll crack your actuator. That's generally how my things break. So yeah.
Is there a limit to the sun rating you use for your cells? Like, why not 100 sun rating?
You could, but they'll heat. So a lot of the issues that I've seen with other people who are doing laser power intensity is you need a pretty large heat sink on the back to make sure that you don't fry your cell. And that happens pretty quickly.
But 3 suns is not going to overheat.
3 suns doesn't overheat the cell. Yeah, and we're still pretty far away. Yeah.
As much as the fabrication process becomes complex, it inspires me how the biological system is, well, very effective in, storing the energy, transmitting to the mechanical energy. So, and also it was great to see the table that was the mass power payload. So
Yeah.
could you give some insights if you compare this with a bee?
Ooh, interesting. I don't know much about the payload capacity of the bee. Our mass is similar. Flapping frequency is similar. I don't know much about how to translate the idea of electrical power from chemical power, like because they're eating sugars and turning that type of energy. I know like based on our mechanical performance that we're quite similar to what they can do. Like our max speeds are very similar to bees' max speeds. Like I think we can go up to like 40 centimeters a second in wind. And at that point, bees will also just say, it's too windy, I'm not flying today. They don't say it like that, but we just don't see a bee go outside past a certain point. But I'm not sure about the overall power. It's an
This
interesting
being
question.
of course, material science grows together.
Yeah.
And battery science also goes together. Do you
Yeah.
think you can make bee-like behavior. You can store the energy enough so they can fly over hours.
Yeah.
If batteries goes better or actuator goes better, or do you think you are looking for most like system that can actually convert the chemical energy into
Yeah.
mechanical energy?
So that was something that we started looking into with the explosive jumper that Cam Oven was looking into, and how we could actually improve force performance with like onboard chemical sources instead of electrical performance. I think that becomes a very interesting systems problem because you still need an electrical source for any type of control or sensing system that you're putting on board. So it becomes this like multifaceted problem where you have to like carry multiple sources of energy in order for like an autonomous robot to actually move through a system. And so we had a lot of interesting conversations about like, yeah, sure, you can do this untethered, but now I need to put a camera on board, or I need to put cameras. You don't need to put cameras on board. You need to put other sensing systems on board. Those will still require electronics. So, yeah.
All right, well, thank you
Okay.
again, appreciate it.
Yeah.